Okay, so hello everyone. Uh, Welcome all of you. Uh, I am Arjun, and on behalf of STEM and Space, I'd like to welcome you for a webinar on Aditya Mission. So here we are to celebrate the World Space Week. And to do that, for our webinar today, we have Dr. Dipankar, the Director of Aries Observatory, and Dr. Mira Mitra, the Chief Scientific Officer of STEM and Space, with us. So right now, I'm going to hand it over to Milama to please start the webinar. So yeah, Milama, over to you.
Mila, you have to unmute yourself.
Yes. So you're
So,
mute.
right. So, hello, everyone. Uh, on behalf of STEM and Space, let me welcome you to World Space Week. We are celebrating World Space Week from October 4th to October 10th. And that World Space Week is a UN organized event which is celebrated all around the world. Everybody celebrates it at the same time. The purpose is to popularize astronomy and make people aware of what astronomy and space is bringing to the world. Today, I welcome Dr. Dipankar Banerjee. Thanks for being with us here today. And with me is also Arjun Gulia, uh, also my colleague from STEM and Space. So World Space Week 2020 has the theme of satellites and how satellite has benefited mankind. So with that thought in mind, we have Dr. Banerjee with us here today, and he will be talking to us about the Aditya L1 mission, which is the first Indian mission to the sun, or the first Indian solar mission. So satellites help us in so many ways, in communications, in remote sensing, in satellite data, in agriculture. So today we'll hear one aspect of it from Dr. Dipankar Banerjee. So we are so privileged to have him here with us today. Dr. Dipankar Banerjee has been recently appointed as the director of the Aryabhatta Research Institute of Observational Science, in short, ARIES, in Nainital. He is an astrophysicist, also who has been working in Indian Institute of Astrophysics for the past 15 years. He has a bachelor's degree in physics from St. Xavier's in Kolkata and master's degree in theoretical physics from University of Kolkata. He has obtained his PhD from Indian Institute of Astrophysics and has completed his postdoc at reputed institutions in Europe. His area of interest is the sun and the solar atmosphere. His work involves theoretical and numerical modeling using data from ground and space-based instruments. His work has enriched our understanding of the sun and its impact on the solar weather. He is the head of the science working group and co-principal investigator of the Coronagraph payload to be launched on the Indian satellite Aditya, which is an ISRO mission. It is the first dedicated Indian mission to study the sun. He's also the project coordinator for the National Large Scale Telescope Project, which is a 2-meter ground based telescope which will be installed at a Himalayan site. He's also involved with NASA's Punch mission. He has more than 100 peer reviewed publications. He's a member of various scientific organizations like Royal Astronomical Society of UK, International Astronomical Union, Solar Physics Division of American Astronomical Society, and so on. He actively participates in outreach programs to popularize science education, traveling to the remote corners of the country. And of course, he has various other interests. He's an avid follower of sports and was on the Indian Institute of Science football team for 5 years. He's also trained in Hindustani vocal and participates in various musical programs. So he's interested in photography and traveling. And he has traveled from Easter Island in Chile to mountains in China, always chasing solar eclipses. He has the privilege of observing the solar eclipse from an open hatched military aircraft. So we are so happy to have him here with us. And welcome again, Dr. Banerjee. And I welcome you to share your ideas and your insight about the Aditya mission now.
Thank you very much, Mila. Thanks for inviting me and giving me this opportunity, this platform to interact with young students. So the young minds are most important for taking science forward. Unfortunately, we have difficult time. I would have loved to, meet these young kids face to face. But whatever we can do now with this new normal, let's try this way. So let me just uh, get into my research talk today. So I will be introducing you to this mission which we have for the studying the sun from ISRO. But before I could talk about this mission, I would like to tell you where I'm coming from. My little background, thanks to Mila, she has already given me a big introduction. But just to excite you about the places where we move around or we work professionally, I want to share some pictures on that. And then I will introduce very briefly about some features about the sun, interest on the sun. Based on that only, I can talk about why we have a dedicated solar mission. So just to make that connection, that why do we need to study the sun, in what context, I will have a few slides, and then the last part will be dedicated to different payloads and a little bit of description of those instruments and so on. First of all, my roots are with Indian Institute of Astrophysics. So what you see pictures here on the left side, the top one is a Himalayan Chandra telescope, is situated in the mountains of Ladakh, and the lower one is the Vainubappu telescope, which is in Tamil Nadu, close to Bangalore, about 4 hours drive. So these are our bread and butter instruments on these telescopes which we use. And more recently, I have joined Aryabhatta Institute in Nainital. And this is a telescope, 3.6 meter, the biggest of this kind from this part of the globe. I will briefly talk about that. So the top picture again shows you where is my office. So this is a Manora Peak, about 10 kilometers south of Nainital city. And this is our campus here. And more recently, we have a new campus called Devasthal, which is 50 kilometers east of Nainital. And this is the largest telescope from this part of the globe. I will be showing a little close pictures. So here we are in Manora Peak. This is one of the oldest telescopes in the country, 1 meter, still functional on a daily basis. You can, today evening, the sky is very clear. You can go and observe certain objects. We also have a 50 centimeter solar telescope, which is operational from 1993. And this is a 50 centimeter split telescope operational from 2009. And that's my window here of my office in the top of the hill. This is a close-up picture of this telescope, which is more than 50 years old and still functional. This is a German telescope. And this is the solar one. It has H-alpha filter. I will talk about H-alpha probably later on, which looks at the atmosphere of the sun and looks at dynamic events like flares, which happens on the sun. This is a close-up view of Devasthal, which is about 2.5 kilometers above the sea level. This is the telescope I was referring to, which was inaugurated by our Prime Minister Narendra Modi ji in 2016. We also have a 1.3 meter telescope, which is operation for almost a decade now. And this is more regularly used for imaging and so on. We also have a very unique new telescope, which is from the concept of a built from a liquid mirror. essentially, we need mirrors for reflecting this light from the sky. And if you can, have, say, Mercury and rotate it at a very high speed and create it in the form of a mirror, it's much cheaper than traditional mirror telescopes. And that will be inaugurated, or sort of we are expecting the first flight in 2020. We were already all scheduled during this last summer, but because of the current COVID conditions, the people who are responsible for final first flight couldn't reach Devasthal. So we are now scheduling this for the late half part of this year. This is the 1.3 meter telescope, and you can see the beautiful Himalayan mountain range from in the background. So you're most welcome to visit us when situation prevails. This is the 3.6 meter Devasthal telescope. We call it the nation's pride now. And again, beautiful sky. Today, observation will start in few hours. I'm just in continuous contact with the observers tonight. They're sitting with multiple instruments in the back end and so on. Very exciting time. So that's the background where I am from. I will get into the subject of our sun, our nearest star. The sun, like all other stars, is a very dynamic star. Although you just see this sun as a sort of a face in the sky, bright, and apparently you probably do not notice that there are so much of dynamic activities which happen in the atmosphere of the sun, or the surface of the sun. When we look at closely with the high resolution telescopes and instruments from ground and space, we see these dynamics. So what is happening is there is always some changes happening in the atmosphere of the sun. And this change is of different time scales. Sometimes you see changes of the order of seconds, minutes, hours. You see, this is an example from a telescope in the Solar Dynamic Observatory, looking at the coronal layers of the sun. So these are the outermost layers of the sun. In fact, incidentally, the name corona has come from solar corona, because the virus looks very same as total solar eclipse images, and that's how the name is. Sun is not responsible for the generation of these viruses, though, but the name has actually derived from solar coronal images taken from eclipses. It looks very similar like that structures. So what I'm again trying to emphasize here is how dynamic the solar atmosphere is. This is an event, there is a sort of explosion happening in the atmosphere, and you see large amount of material is thrown into the interplanetary space. Some material is falling back into the sun, if you see this in this movie, but the rest of the material actually travels through interplanetary space and then reaches Earth. So there are two things. One is in between space also, if there is a satellite, the satellite directly gets impacted by these radiations and material and the high energetic particles and so on. So the satellites can be badly damaged. The other thing is they can travel farther and then again impact with Earth's atmosphere as well. Fortunately, Earth has its own magnetic field. So we are actually shielded or protected because of the presence of Earth's magnetic field. But sometimes, some large number of particles can escape these magnetic shields and can reach. Particularly, there are reasons why it reaches a certain point of Earth, not everywhere. But if it reaches, then it will impact with with electrical transformers or any devices or any spacecraft. Any airplane which is flying through the polar regions all the way to US, for example. So we have to worry about all these effects. So to understand when sun can explode or this kind of events can happen, we need to understand first why these kind of events are occurring in the sun. Now, what we understand is it appears that the magnetic field on the sun is primarily responsible for all these changes. So as I mentioned, the changes are of different time scales. Sometimes you see such dynamic, very transient, we call it transient phenomena. There are changes over years also, or centuries as well. So that's again another branch of study which I also do quite a bit. from data taking from different observatories over centuries. So we have to go back to the historical archival data and find out what were the changes in the sun happening. So this is a few introductory remarks of this. So Sun is a normal star. It is a middle-aged main sequence star. Don't have to worry about the spectral type and all that. It allows us to classify different types of stars. But the most important element is Sun was born from interstellar medium. Some particles, they started coming closer and then they form a star. And it will still continue into that same kind of state inside that star for many, many years, millions of years. We don't have to worry about it. It's like, all human beings, we are born and then we undergo a evolution. I mean, kind of we go through our different stages in the life. Sun also as a star will undergo these changes. Of course, it is a spatial star because it is the only star on which we can resolve the spatial scale on which fundamental processes takes place. I think this is a very important element because most of the objects in the sky, you study them as a point object. You really cannot see so much of details, on the surface or in the atmosphere and so on and so forth. Sun being closer to us, it provides us the unique opportunity to study this amount of detail. Of course, it is a spatial star because it provides almost all the energy to the Earth. You see, our existence is because of we are appropriate distance away, and of course our magnetic field also. So there is, conditions, these days there are a lot of, discussions about the habitability. Is there a possibility of life in other planets? We are actually discovering solar-like systems in other places also, in other galaxies as well. So is it possible to have life in other, solar system-like systems? That all depends on, how far the planets are and then the planet's atmosphere and so on. The other thing is very important as far as from my background is it provides us with a unique laboratory in which to learn about various branches of physics. Because as you heard, I come from a physics background. My interest was what kind of physics I can apply to the study of the sun. So I found out, there is all branches of physics. I mean, you start from nuclear physics, atomic physics, molecular physics, particle physics, plasma physics, you name it, almost, sun has provided a unique opportunity to study that branch of. Because what happens is any physics remains as a hypothesis until you verify them in a laboratory experiment. But now, certain conditions is very difficult to achieve in the laboratory. Suppose I want to have a temperature of millions of Kelvin. I want to have a magnetic field of, kilogauss, to have a few gauss of magnetic field and a very strong electric field, magnetic field in the laboratory itself is very, very challenging. So if you want to study the physics in those conditions, you have to think about a laboratory which is there in the sun. So for example, the sunspots, these are large magnetic concentrated regions on the sun. They have, magnetic field of several thousands of kilogauss. So that means thousands of gauss. So that means, that natural condition of plasma physics, which I want to study, is there in the sunspot. So sun provides a unique laboratory for studying that kind of feature. The sun is located in the spiral arm of our galaxy. This is the so-called Orion arm, some 30,000 light years from the center. The sun orbits the center of the Milky Way in about 225 million years. The solar system has a velocity of 230 kilometers per second. So these are some of the numbers, but the fact is these numbers shows also how fascinating this object is. See, our own galaxy, which is called the Milky Way, the picture what you see here on the screen, has 100 billion other stars. To think about it, I'm going to talk about only one of these stars, which is the sun. And there are about 100 billion other galaxies. So, there are plenty to learn from the space. The sun has inspired mythology in many cultures, including ancient Egyptians, the Aztecs, the Native Americans, Indians, and Chinese. So this is again, if you want to go back to the history of certain things in the atmospheric thing, even the development of physics, discovery of telescope, everything has a link with how the study of the sun has progressed. Sun has 333,000 times more massive than Earth and contains 99.86% of the mass of the entire solar system. These numbers again gives you a clear indication that in a many body system, the sun, how heavy it is. So you can imagine that the most of the dynamics will be controlled. The center of mass is very, very close to the sun. So obviously the other small little perturbations in those other small bodies in this entire solar system will not affect actually sun much. We can directly visualize that. And as I mentioned, sun is in the middle age. There is actually a process called a nuclear reaction whereby hydrogen gets converted into helium in the core of the sun. And then the hydrogen, as you can see here from this number, there's still about 78% of hydrogen and 20% helium and 2% of other elements. So as sun gets older and older, the hydrogen content will get slightly depleted. The total energy radiated is, can be considered as 100 billion tons of TNT per second. So TNT is a unit for a thermonuclear reaction kind of thing. You can imagine that there are 100 billions of hydrogen bomb which is being exploded inside the sun every second. So we are actually fortunate to be away, to an appropriate distance. So this is now I will come mostly in the atmosphere of the sun. I will talk about it. So the visible surface, what you see in the sky is called the photosphere. These images are mostly what I will share with you is taken from different space platforms. So here there is a pair of sunspots. As I said, sunspots are strong magnetic field regions. And what you see here is two polarities of sunspot. And then the surrounding, you also see a sort of granular structures. It's like a cellular network kind of structure. This is a direct manifestation of convection. Sun underneath the surface is actually in the convective state. You are familiar with, if you start boiling a soup and if you notice the top surface, you will see that there are some kind of network pattern which forms. This is because once the soup is completely boiling, then material goes up and the hot material comes up, the cold material goes down. So this sets the convection in a bowl of soup. Exactly same thing happens in the sun as well. So these cellular structures are showing that sun is convective underneath. Now, if I go a little higher, say about 1,000 kilometers above the surface of the sun, what you see a picture. This is taken again from the space with a calcium filter. I will talk about this later on again. To probe this, say, typically 1,000 kilometers above the surface, and you see this still the same sunspot pair, but the background picture is slightly different. You see another bigger structure here. These are called supergranules. So the one which we are seeing in the background is still the granules are still there, small structures. But here the supergranules seems to be dominating the brightness image of the chromosphere, and still the sunspots are visible. If I go slightly even higher and take an image with the H-alpha filter, this is again a hydrogen line which is formed in the upper chromosphere, say around 1,400 kilometers or so. And then you will see the structure of the chromosphere is more filamentary type. You see long elongated filaments like structures. Of course, you still see the sunspots. So it directly gives you information that this sunspots looks like a pillars. They are there. They are anchored in the surface or probably much deeper inside the sun. And then around these kind of pillars, the structures are changing. The distributions are changing as we go higher up in the atmosphere. If I now go to even higher up in the corona, several thousand kilometers up, this is the image taken from, again, X-rays, shorter wavelengths. You still see the dark sunspots in the background, but you see more elongated, longer kind of structures. So these are called X-ray loop-like structures and so on. So as I pointed out, we know now the sun has magnetic field, and it appears that the presence of the magnetic field, where the magnetic field concentrations are, dictates the distribution of different structures and also the brightness of the sun and so on. Here, again, this is an extreme ultraviolet image taken from a space platform. We are looking at a coronal height. Here you see that wherever there is a underneath strong presence of magnetic field in sunspots, the things are bright. That means large amount of plasma material is confined into these regions. And how they're confined? They're confined because of the presence of the magnetic field. And now we understand, and in these kind of regions, the magnetic field is more closed loop-like structure. So here, this is a theorist, diagram or cartoon, which depicts the topology of the magnetic field or the connectivity of the magnetic field. As you know, in your lab, when you have a bar magnet, you have a north pole and a south pole, and they're connected by magnetic field lines. So here, these are depicting the magnetic field line. So wherever there is a strong magnetic region, their connectivity seems to be closed in on the disk. Whereas if I go to the polar region, you see here the brightness is slightly lower. So it appears that it's slightly probably cooler than the surrounding as well. These are called coronal hole, and their magnetic field line seems to be more open structure. And again, there is a bright region here, there is a bright region there, and all of these places we see that the magnetic field lines are more closed in nature. So this is what is controlling the movement of the particles or the plasma, which is confined in these regions. So as I was mentioning, that we can imagine that there is a huge bar magnet. This is again a drawing of Earth's magnetic field. So the Earth's magnetic field, there is also another interesting aspect is, you see all these celestial objects, they also rotate about their own axis. So the rotation axis and the magnetic axis are not always aligned. If they're not aligned, there are furthermore complications can happen. So this is again another interesting aspect. So here what you see is that the magnetic field lines, as I indicated in a bar magnet also, it comes out of the North Pole and then it connects into the South Pole. Now, another interesting aspect in the sun is, I will not talk about very detail in today, but this magnetic dipole, what I have indicated, it can flip also. And as you can imagine, if it flips after a certain period, then of course this connectivity and the directions and all that changes. So in the case of Earth, actually, we do not know precisely what is the periodicity, because it takes probably a million years from the theoretical our calculations. But in the case of the sun, this flipping happens every 11 years. So that again, a very interesting aspect of polar field reversal in the sun. In fact, I just published one article today in one of the journals there about this polarity reversal. So again, what I'm trying to drive at is the study of the magnetic field seems to be the most interesting aspect on the sun, and that allows us to understand the dynamics also. Here, the other difficulty in the magnetic field on the subject of the sun is that we do have direct observational evidence or measurements of the magnetic field on the surface of the sun. Unfortunately, as we go higher up in the atmosphere, we do not have a very reliable, regular magnetic field measurements on the sun. So this is again one of the key science objectives of the Aditya mission also. We are making an instrument to do that. So far, what we have been doing is we are only depending on the theoretical extrapolations and theoretical understanding. So this is again a theorist extrapolation. What it shows is that probably in the sun, the magnetic field lines are connected somewhat like this. This is based on a mathematical model and potential field extrapolation. And if I compare with observations, doesn't seem to be that the observations seem to show similar indications are there. So these images are taken from, again, satellites. These are extreme ultraviolet images. These are, as I can say, that these are called coronal loops. The plasma is confined. These are like rubber band, you can imagine, right? You're familiar with this, picture. So it appears that this rubber band kind of structure, all the way permeating into the corona and so on and so forth, matches reasonably well with the mathematical model, which is, theorists are giving. So this is again another sort of demonstration how we work closely with our theoretical understanding and the observational, findings. As I indicated earlier as well, that any science becomes a postulates or hypothesis, until you prove it under laboratory. So since these conditions are not achievable in the laboratory conditions, we look for astronomical sources to verify our theory. So this is again another clear example why we look at the sun is to study the behavior of the plasma physics with the presence of the strong magnetic field. There are storms in at the source. So when magnetic forces above sunspots become tangled and break apart, you see here in this movie, violent storms can burst from the sun. These are called solar storms. This is the main source of our strongest space weather event. As I indicated in my opening remarks, that we need to study these events which affects our weather in the space. Because if you have a satellite launch, or if the satellite is moving into this kind of environment, you can imagine it will be completely damaged. And this white little specks, what you see here at the end of the clips, are actually protons from the blast hitting the spacecraft imager. Because these images have been taken from a satellite which is sitting in the Lagrangian one point, where Aditya also will be going. And you can imagine that this detector or this imager, your mobile camera, is looking at the sun or taking continuous images, and suddenly this white shower comes. These become very highly energetic particles. They will destroy your camera completely. So we need to know how to protect these instruments, and then if such events come, we have to shut down our system to protect this satellite. So this is one of the major drivers what we have. Here, what you see here is, again, there is a flare. These big loop structures, they are strangled and so on, and then they expel these material which were confined within these magnetic loops. Flares are quick, intense, and smaller explosions than coronal mass ejections. What I am showing now here in these movies are called coronal mass ejections. Essentially, again, in this movie, you see that there is this kind of huge explosion on the sun. So this is a close-up of these explosion here. As I was also trying to show you in the beginning, that we take images by different filters. So different filters, or which is actually probing different layers of the atmosphere, allows us to study the behavior of this event, how it propagates when it travels through the atmosphere into the interplanetary space, and so on and so forth. That's why it is very important to have many filters. You can think about many different colored glasses, and some of you are familiar with the 3D pictures. What it does is actually it converges the images taken from different different filters, and then it synthesizes that. So here also we look for images taken at different wavelengths, which is probing the different layers of the atmosphere of the sun. Here again, this movie is showing you here that this is the flare, which is seen from the 304 angstrom filter, which is probing the chromospheric heights in the thing. And then you have these huge explosion material you saw, it was going out. So if you are going out, then of course you have to look at some other instrument, which I will come. So this is taken from 171 angstrom image, which is probing the coronal heights. As you see here, that the same material seen in the corona looks slightly different and so on. But now we have to follow these structures to the outer, extended atmosphere. So how do we do that, and all will come in the next slide. So here what we will see is the CMEs, which is large solar storms that can blast out of cloud of billions of tons of particles at over 2 million kilometers per hour. So here in this movie, you will see that this is a huge explosion, which is recorded from, again, chromospheric heights, but then some material fell back into the sun. Some will go out of the sun. Then what happens to the outer atmosphere and all that we will see from other images, which will come next to you. So these clouds reach Earth's orbit in about 1 to 3 days, depending on the propagation speed of this material. It will take that long. So now we need to predict, if we see such an explosion happening, then whether it is going to come and hit us And when it is going to hit us, this is the kind of work which we do. This is what called the space weather prediction. And this will allow us to save our, space real estate as well. So here you are seeing again a full disk image and this particular explosion which we are talking about. Now what is shown here is we are blocking the solar disk. This is an instrument called Coronagraph. This is very similar to the total solar eclipse kind of condition. So during the total solar eclipse, the solar disk is blocked and we see the extended atmosphere. So here it is a combination of, I will pause this, so a combination of two different coronagraph. One in looking at the close to the sun. This is again in the solar and heliospheric observatory called SOHO, which is again at the Lagrangian 1 point situated, and we have been working with this for the last 20 years. And as you see these CMEs as it propagates, you can imagine, these kind of material, and I'm sure you will not like to be somewhere situated here to impact this, a huge object. And these objects do travel all the way to us. So what is important is to study these, coronal mass ejections from multiple satellites, multiple vantage points. It's again, this is an example from another coronagraph on board a stereo spacecraft. This is again a NASA spacecraft to look at this explosion. And then when we have, images from multiple vantage points, we can reconstruct those images to study the properties better and so on. So that's a sort of, kind of things we would like to do. And so this is another good example of a CME observed by stereo spacecraft. And as you can see that these guys are moving all over, and if you happen to be there, you are in trouble. So this is the subject called space weather, which we are going to study from Aditya as well. But as I indicated, that sun has its own magnetic field. Normally the solar magnetic, Earth's magnetic, not sun, the Earth also has its own magnetic field, and it protects us from the solar radiations and the particles. Because of the solar wind, the original configuration, which was something, would have been something like that if sun would not have been there. Now that gets completely changed because of the solar wind and this different particles which comes in the form of CMEs and so on, and that changes the Earth's magnetic field structures, Earth's magnetosphere, which is called, which is depicted here by this green lines. This is again another huge subject area where people are working. Now I will move into Aditya's descriptions, but before that I will just point out, why do we need Aditya mission? As I think you got a little impression that when we look at different wavelengths only, we are able to see the emissions from different layers of the atmosphere. If you would have only the telescopes in the ground, then you could have only seen the optical wavelengths. So as you can see here in this electromagnetic wave, which is shown here, if you restrict, our eyes can only see optical wavelengths. And this is a sort of image of a sun taken from a white band filter from the ground. If I take an image in infrared, I do see a little bit of structure, because infrared allows us to look at the chromosphere. But if you want to look at even higher and higher layers of the atmosphere of the sun, you need to have shorter and shorter wavelengths. So that means you need to have UV. This is the image taken from a UV telescope, and this is the image taken from a X-ray telescope. So point is that when an object goes to higher and higher temperature, it starts radiating in smaller and smaller wavelength. This you know from your classical experiments as well. So in general, if you really want to study astrophysical objects, as you know, most of these astrophysical objects are at a very high temperature. They all emit in very short wavelength. So you need to see the UV and X-ray emission from them. Of course, you can have radio telescopes. This is the longer wavelength limit, and then radio wavelengths can penetrate Earth's atmosphere, so no problem from ground observation. But UV and X-ray is completely blocked by Earth atmosphere to protect us. So if you really want to understand any astrophysical scenario in its completeness, and that is not different from the sun, you really need to go to space. And once we started going to space, our understanding of sun has completely revolutionized, completely changed. I must tell you, I started my research career in early 90s. That time, it was just the beginning of the space solar missions. There were small missions earlier, but SOHO was a mission which was launched in 1995, which went to Lagrangian 1 point with 13 instruments, combination of remote sensing and in situ. I will talk about it. That changed the entire subject altogether. And we are hoping that with the Aditya mission, we will be able to do that in the context of the of Indian solar physics as well. So Aditya is India's space mission. This is again a multi-institutional, and ISRO's many different centers and bodies are closely responsible for that. So this is a wholehearted Make in India, Made in India mission. Every payloads are getting manufactured, are completed within Indian institutions with the help of ISRO, completely funded by Indian government. So I think we can feel very, take a lot of pride about this. We hope, of course, the mission, the payloads are still getting built in the laboratories. And there are 7 payloads. I will briefly talk about these 7 payloads. This is the Coronagraph to study the parameters in the solar corona and studying these dynamics and the origin of these coronal mass ejections, what you saw, these huge explosions, how it travels into the interplanetary space and so on. It has 4 cameras with 3 visible cameras and 1 infrared cameras. We are also attempting to measure the magnetic field in the corona from the first time from space. So this is being built in Indian Institute of Astrophysics in our campus in Hosakote. Currently, the instrument is getting assembled there. Then we have a near UV telescope, which is going to look at the full disk images, which is built in Pune in Ayuka. It is finally going to be integrated at ISRO in Bangalore, which will have many filters to look at different layers of the atmosphere of the sun. So, as I indicated that when you look at through different colored glasses, you see different layers of the sun here that will be attempted, but not in the extreme ultraviolet, which is normally there with the other space missions. We are looking at a different wavelength region near UV because systematically that has not been seen earlier. So this is going to be a unique experiment from space. There have been balloon and short rocket experiments, but not a continuous space program for this. Then we have particle detectors. You see, as you can imagine, we are sitting in a position called Lagrangian 1 point. This is almost like a 1% distance between the sun and Earth. So 1,27,000 kilometers we'll be traveling from Earth, and we'll be rotating around that particular point, continuously looking at the sun. So anything comes out of the sun, before it reaches Earth, it has to hit the satellite. So the idea is that you can continuously look at the sun and take images on the sun, calculate the total flux or energy which is coming from the sun. These are called remote sensing instrument. Also, you can have in situ instrument. That means if a particle comes, it hits the satellite, means there are probes. It will detect how many particles are being hit and what are the properties of these particles, what kind of charge state are there in this particle, what kind of particles it is, whether it is electrons, protons, higher ionized things and so on. What is the kind of magnetic field for these particles are carrying? So these kind of instruments are also there. They are called the in situ instrument. So such one instrument is this called Aspects, which is built in Physical Research Laboratory in Ahmedabad, which has this kind of energy range, 20 keV to 20 MeV. Then also there is a slightly lower energy particle detector called PAPA. This has been built at a Space Physics Laboratory in Trivandrum. Then we have 2 X-ray payloads. These are spectrometers as well. So apart from calculating the total flux, what is coming in X-rays within this kind of wavelength or this kind of energy range, it will also give you indication what kind of elements and what kind of elements in different ionization state it can have during these high explosive phenomena like flares happening in the sun. So we have a higher energy spectrometers also, as I indicated. The lower energy spectrometer has this kind of energy range, and the higher energy spectrometer has a range 10 to 150 keV with some overlap for cross calibrations. And we also have a magnetometer, as I indicated, that a magnetometer is an in situ instrument going to be situated at L1, which will detect the magnetic fluxes or changes when a CME passes through the satellite. So this has been built by Laboratory of Electro-Optic System called LEOS of an ISRO center. So this is the different payloads, the location in the satellite. This is the big elephant, the Coronagraph, 170 kg odd, and the sitting in the top deck. And the next is this imaging telescope, and then the other small, payloads are at different locations as indicated in this diagram. So what we are going to look at is this portion of the sun. So the background image is a total solar eclipse image taken more than a decade back. As you can see, there are beautiful structures in the corona, fine structures, which are, again, this is a static image, which changes with time. I mean, at different phases of the solar cycle, different times, this will be very different. I will show some example. So this is the field of view. We are going to focus very close to the sun, because when this explosion happens, how to track these explosions and the material when it travels through the interplanetary space is our goal. We will also have a spectrometer or spectroscopy experiments. I will not talk about it, but if somebody has a technical question, I'll be happy to answer that. So these are called multi-slit experiments, so that you can probe the plasma conditions in different locations in the sun. So this will give you the temperature of this location, and this temperature, how it changes with time and so on. So with those kind of combination of imaging and spectroscopy experiment, you can get a better handle on the plasma conditions and the atmosphere of the sun, namely the corona. Here, what it is showing is there again, you see that there are two images which are overplotted on each other, taken again from two different filters. As I indicated, this is taken typically at a red filter and a green filter. And as you can see, the corona looks in the solar eclipse time 2006 and 2010 time is very, very different. The coronal structure patterns, the petal kind of structures are very different. Also, what you see is the corona, what is seen in the red line and what is seen in the green line always is not overlapping each other. That means, the corona is multi-thermal and so on. So all these, different kind of properties we will be able to study. And as you can see in this image, there is a lot of changes happens in the sun in longer time scales as well. So as I indicated in the beginning itself, that the atmosphere really is a variable and of different time scales. So to study these different time scale, you need continuous data, because solar eclipses happens for a few minutes, and then you have to travel into the other part of the globe with small little instruments and so on. It becomes very, very challenging to do that experiment. So here in the space platform, we are continuously looking at the sun. So that will give us an enormous amount of new information. This is showing you that there is a propagation properties of this coronal mass ejection, what I have talked about. What is shown here in the top plot is called height time. As these coronal mass ejection propagates into the interplanetary space at different, so this is a theoretical understanding of the propagation. Here what is plotted is from these observed locations in the coronagraph, from these two coronagraphs, the velocity is being plotted like this and the acceleration. But what is to be noted here, why you have included this plot, is these are observational data. We do not have observational data very close to the sun. Here also you see there is no observational data at all. So this is our theoretical understanding. Who knows that this is like this? It can be like this also, na? So there is no guarantee that it will be like this. So to verify this, this our physical understanding, how the coronal mass ejection propagates into the interplanetary space, we need data points very close to the sun. So our coronagraph from Aditya will be, for the first time, will be able to systematically, regularly be able to provide data within these regions. So this is again another huge subject area which we will address from Aditya coronagraph. And then this is the global structure of the corona, which is again, as I indicated earlier, as well is theoretical understanding what we have from magnetic modeling. One of my colleague, Professor Nandi from ISER Kolkata, does these kind of experiments in his computer lab, and he verifies that with eclipse images. So this is a prediction actually what Dipindu did just a few days before the total solar eclipse. So he published the image, a couple of days before the solar eclipse, and then the eclipse images were compared, which turned out to be quite good as well. But when we have regular observations, so these models, whatever differences he found, can be further improved. So this is again another area where we will be actively working with our Indian colleagues. So that's sort of my excitement and my experience I wanted to share. This is where we are going to go. This is called the Lagrangian 1 point. This is a sort of, there are 5 different Lagrangian points in a 3-body system. And as you can see here, we are at the Earth. So if anything comes out of the sun, as I was indicating, it has to first travel through the L1 point. So that's the advantage of reaching at L1. This is exaggerated. This distance is not really that much. It is only 1% of the sun-Earth distance. Just for showing it, it is shown like this. The top panel, what you see is our Hanley Observatory with many beautiful features. And this is a gang of students I have. We are all working at different areas of solar physics, and waiting for the Aditya Mission, which is expected to be launched next year. Our progress is slightly, sort of delayed because of this current situation. A lot of experiments and communications have been hampered during this COVID period. But we hope that we should still be able to launch, Aditya by sometime, definitely by first half of next year. So that's the hope we have. And thank you for your attention.
Okay, thank you very much, Dipankar sir. So this was a very interesting session from you. So now I would like to ask Mila ma'am to share her thoughts, and then so many viewers were joining us on the YouTube platform, and we have got many very relevant and very interesting questions for you. So I would like to ask you those. So yeah, Mila ma'am, please go first.
Sure. Yeah, thank you for that session. It was very informative, and we learned about space weather and about the sun, in addition to what Aditya will observe and what kind of payloads and information it will give to us. So we are very excited about learning about it. So yes, go ahead, Arjun, please. The students are very impatiently waiting, so we can take a few to Dipankar sir.
Sure.
Yes. So the first question is asked by Anjali Joshi. She wants to ask, sir, can you please tell how Aditya L1 will protect itself from the hard solar wind?
Okay, yeah, very good question. So as we were always indicating that, this continuous, particles and radiation is coming. So to tell you, any space mission for that matter, and particularly since we are always looking at the sun, we have to have, have to choose certain elements, certain, structures and certain properties of the material, which will be, will be good for this hardening. So what we do is any small little things which is chosen for building this instrument is bombarded with particles in the laboratory to see whether it can sustain or not. So this is called hardening of the each component, whether even electronics, any component which you use, it should be space qualified. So in fact, any instrument what you build in the ground costs only 10% than what it costs in the space. So the space experiments are always 10 times more expensive because of the same element. You start with taking hundreds of these small little, any component, you take it to the lab and make the space qualification. Only 10% actually gets qualified. Others are actually thrown away. So this is an exercise which has to be done for building any space instrumentation.
So adding to that question, I was also listening very attentively. So I got one from one of your points that when the mission is to be placed in the L1 point, and sometimes we have to basically we have to shut down our equipments to save it from to protect it from the harsh solar winds. So my question to you is, how can we detect that a particular solar wind is going to come? Because sometimes they can be abrupt. So can we map those kind of solar winds to make sure that, okay, so at this particular point, so this is going to come, and we can basically close the instrument there, or how we do that?
Yeah, so the fact is the solar wind is a continuous expansion. So the coronal mass ejection is the intermittent, portion of these material which come. So obviously we have a more definite knowledge about how the solar wind properties are at different phases of the solar cycle as well. So there is some variation, but we know roughly what is the fluxes, what is expected and all that. What is not more accurately known is the CME thing, because the CMEs also can have a speed of 100 kilometers per second or also 2000 kilometers per second. So these 2000 kilometers CMEs only happens once in 2-3 years or even sometimes 5 years. So they are rare things. So we have to, but at the same time, we want to detect them.
Yes.
So if we close our cameras and so on, then we miss the opportunity of detect those, spectacular events. So we have to make our instruments ready for that. And we sometimes do take risk of observing this. So, but normal, what I was trying to say, this is dedicated solar observing, mission. But if there is a commercial satellite for telecommunication and all that, they are not equipped with this kind of protection element. So they get damaged, their solar cells get damaged and so on and so forth. So in our case, we are dedicated for this study only. So all the components have been, prepared and ready for this kind of hard radiation. Whereas a commercial satellite, which is just launched for, say, communication purpose and all that, they are not always, equipped with this kind of sophistication.
Yes. So okay, so I'll go on the next question. So the next question is asked by Mokshi Agarwal. So she is asking that why is Corona too hot in comparison to the other layers of sun?
Yeah, this is a very good question, and this is called a coronal heating problem. And since you have asked this question, way back in 1990 when I started as I said, after my master's, that was my project, and I'm still working on it. So the point is, so this is a very good question to tell you, why this is a puzzle. Because normally when you are going away from a hot object like sun, because the thermonuclear reactions is happening in the core of the sun. So there the temperature is tens of millions of Kelvin. As you come to the surface, it is 6,000. But when you go away from the surface, you expect the temperature to be lower. As it happens in the Earth also. You go to the Nainital or to Devastal, the temperature drops. And if you go further up, the temperature is even lower. So this cannot be explained by a normal thermodynamic processes. So there are non-thermal processes which we understand is responsible for this. There are two mechanisms we know now are responsible for this. One is waves. What happens is in the surface of the sun or even in the atmosphere of the sun, there are a lot of these disturbances that generate a lot of waves, and waves carry energy to different layers. As you can, say, I'm clapping. So when I'm making this pressure perturbation, it generates a sound waves. So in the sun also, there are all these kind of, sound waves which get mixed in the presence of the magnetic field. So they become different kind of magnetic waves. They carry the energy to the higher layers. And then there are different mechanisms which converts this magnetic energy, which is carried by the waves, and dumps it in the form of the heat. So that's one way of doing it. Then another way we understand now is called the magnetic reconnection. What it is actually is, normally the magnetic fields, as I said, there are opposite polarities and you have these magnetic field lines. They will not like to talk to each other. They will always repel each other. That's a property of the magnetic field. But suppose you forcefully, interact them, then what happens is there is a process called magnetic reconnection, whereby magnetic energy gets converted into kinetic energy and heat. So this is again, magnetic reconnection is one method whereby you can convert this huge amount of magnetic energy, which is confined in these huge structures, which I was showing you, this magnetic loop kind of thing. You can imagine, there are, these magnetic loops structures are actually 10 or 15 times, longer than the size of the Earth. So you imagine how much magnetic energy is stored in those, magnetic tubes. And when you convert those, that can provide the energy. So flares are also actually a magnetic reconnection process only. So these two, magnetic reconnection process and magnetic, different type of magnetic waves, supply this energy to heat the higher atmosphere. Very good question.
Yes. Yeah. So, sir, talking about magnetic reconnection, so I have one more question by Nikita Chaudhary, so second year MSc Physics. She want to ask that why sunspots look black?
Okay, this is again a good question. So, since you are in MSc second year, I will try to answer you appropriately. So, as I indicated, so sunspots are strong magnetic field regions. So when there is a strong presence of the magnetic field, there is also a magnetic pressure associated with that. So you can imagine a tube whereby you have a plasma where there is a magnetic pressure and also plasma pressure. So the plasma pressure is again directly proportional to the temperature. So if you even take a ideal gas law, then you know the pressure and temperature are directly proportional and so on. But inside this tube, you have two kinds of pressure. One is magnetic pressure, and the second one is plasma pressure. Whereas outside this tube, outside the sunspot, you only have plasma pressure because you do not have magnetic field. So any tube has to be under a pressure equilibrium. In nature also, things are always under pressure equilibrium. To balance this pressure, so the plasma pressure outside the tube is more. So obviously temperature outside is more as compared to the inside. So as a direct consequence, the temperature inside the sunspot is cooler. That's one reason why it is dark. The other reason why it is dark is this magnetic field actually prohibits the energy which is coming from the lower surface or underneath the sun. Because why the sun is bright? Because of these photons which is coming from inside. But then suppose I have a presence of the magnetic field which actually doesn't allow the propagation of these radiation so efficiently. So it will trap certain amount of energy. That is also another reason why it is dark. So it's a combination of these two makes the sunspot as dark feature on the surface.
I think we're almost out of time, but do you have one more question? I think I had a question that Kaustav Nair and Muskan Vora are asked, what material is it made out of?
You mean the sunspot or the...
No, the satellite. The satellite.
Oh, the satellite. Of course, it depends on very many different substances, because the expansion. If you choose a metal, the coefficient of expansion of this, how sensitive it is for temperatures and so on. So different components will have different elements. There could be of course, there could be certain portions aluminum, so could be titanium. So different metals and elements are used. Yeah.
Yeah. Okay. So one
optics are made of with different glass material and so on as well. Yeah.
Yeah. So I just one more question. So this is a question that at the end you showed that there are 5 different Lagrange points around between the sun and Earth. So out of all these, why are we sending the Aditya L1 mission to L1 only? Why not any other Lagrange point?
Yeah, it's again a very good question. Of course, as you can imagine, the other Lagrangian 1 points, of course, L2 is not suitable for sun because we will not be able to look at the sun. But L2 is very good for other astronomical applications. If you want to, stay away from the sun, you can reach. So you have a dark sky much longer and so on and so forth. So the other 2 locations, L5 and L4, are also very good. There is a reason for L5 being very good is sun is actually also rotating in its own axis, as you say. So if we could reach L5, then we will be able to see the other side of the sun few days before we could see it from here. So in fact, we are very much interested to go to L5. It's a fantastic mission, but as you can imagine from here, reaching L5 is very, very challenging, and nobody has reached L5. NASA is working hard to reach L5 now. So we don't want to fall behind, and we will someday will go L5. So of course, for solar perspective, as I said, the L5 mission has its own value, but it is much harder to reach L5. We'll only be able to take small little, because farther the distance you go, your lot of fuel has to be there. That means your payload sizes has to be smaller. So there are compromises on all these matters as well.
So,
Okay, so yeah, Milam.
are there any lessons learned from Parker, or anything that we are trying to do that is like Parker?
Of course, of course. So there are two things, since you mentioned Parker Solar Probe. So Parker Solar Probe, of course, is going much closer to the sun. I mean, it's but it is a heliospheric mission, means it is traveling closer to the sun, and it is going to probe the solar wind. Since it is going very close to the sun, actually it is not able to look at directly to the sun at all, because the heat which it will experience will not allow any of this instrument to look at this. So Parker Solar Probe, and since it is traveling, towards the sun and taking a long time to reach there and all that, it is able to probe the different locations in the solar wind while it is traveling. So it is dedicated for solar wind studies and heliospheric physics. So to tell you frankly, it will be really good for a complete understanding to combine the information from these different missions. There is another mission called Solar Orbiter, which is again an ESA mission, which is also traveling towards the sun, and this is going out of ecliptic. So it will look at the sun, because we only look at from this plane of the sky. When we go out of ecliptic, you will be able to see the sun from the polar region for the first time. Nobody has seen the polar side of the sun at all. So that Solar Orbiter mission will be a very good complementary mission as well. So in future, we are going to do all these things, have coordinated observations and collecting the information from different instruments and different vantage points, and then combining the science.
Yes, so I think that's,
So yeah, so
Arjun, probably we need to end there. And lastly, when is the mission expected to launch, and when will it reach the L1 point?
Yeah, a good question. So we are hoping that we will be able to launch by first half of next year, and it will take about 2.5 months, almost about 3 months to reach L1. And what happens is, once you reach L1, of course, there will be, a lot of verification phase and so on. And one instrument at a time will be opened and all that. So we expect by the end of next year, we will have some first light images, I would say.
So with that, thank you so much for bringing all this exciting information about Aditya Mission to us. And I think if you look at the questions, Dipankar sir, when you get out of this, you'll see there's so many questions.
Okay,
and
I will go, because I can't go to the YouTube.
I know. So unfortunately, students, we were only able to bring a few of the questions to Dipankar sir.
So you can use, just paste my email address there.
We'll do that. We'll give your email ID so they can ask further, and maybe we can also take our time and reply to some of them.
Sure.
So thanks everyone for joining, and this video will be kept on YouTube, so you can log into it and view it later if you want. And again, on behalf of STEM&Space, I would like to bring your attention, students, that we do have a Cosmic Kids Club starting, which is an astronomy weekly club, and any of you can join that. You'll find further information on our Facebook about it. And also we are launching National Astronomy Challenge, which is like an astronomy and space Olympiad. So again, you'll find out more about that on our social media. So I hope many of you got inspired by Dipankar sir to go into the field of space astronomy and solar astronomy. So thank you again for inspiring our students. Thank you, students, for joining us. And thank you, Arjun, for hosting this session. So with that, I think we are going to say bye to all our students today. Dipankar, would you like to say something?
Yeah.
No, it's been a pleasure for me to talk to the students. I would have, as I said, I would have loved to meet you and talk to you face to face, but I hope I've been able to transpire some of my excitement.
So hopefully we can invite you next year when things are better for a face to face talk.
Pleasure. Yeah.
Right. Thanks, Arjun,
Yeah.
for
Okay. Thank you very much,
hosting the
sir.
session.
Yeah. Thank you. Yeah.
Bye, everyone.
Bye.
Okay. Goodbye, everyone. Goodbye, sir. Yeah. Okay. I landed this one. Yeah. So the live stream.
Yeah. Bye.
I did it.
Yeah.